Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm going to talk about spoken dialogue systems. As Tora said, I've been working on this for some time now. And before I just sort of bring it into focus, let me just say what I think of as being a spoken dialogue system. I come very much from the speech area and worrying about the fact speech recognition doesn't work so great, especially in difficult environments. So I haven't really focused very much on the kind of very rich knowledge domains and the issues of fine-grained semantics and so on. So the topics I work on are still pretty simple, limited domain topics. If you look at a spoken dialogue system and just think of it in block diagram terms, you have something that looks like on the slide here. So going end to end, the user speaks, often a request. There's some application. Most of our work for the last few years has been on finding tourist information, primarily restaurant information, but also hotels and other things, initially in Cambridge, more recently in San Francisco. So a user might say, I'd like a cheap Italian on the east side of town, and there's some kind of semantic decoding and belief tracking takes place, which first of all tries to extract the meaning from what is said in some abstract form, and then maps that meaning onto some continuing state-based representation of what the user wants. Because the assumption here is that for many applications, a single voice command is not going to be sufficient to gather all the information, maybe because it's actually quite a complex query, or maybe it's simply because the speech recognition is so bad it's almost certain that you're going to have to go back and confirm and ask people to repeat things till it's confident that it's understood you properly.
What's ASR?
Oh, sorry, automatic speech recognition. I apologize.
Okay,
yes.
so that gets us to words.
Yes, that goes from speech to users speaking, and ASR goes to words. Yeah. And this is just some arbitrary, simple, abstract representation. Now, if you're in a dialogue situation, and what this is, again, a bit cartoon-like, but it's meant to illustrate the sorts of representations we're thinking of. So if it's in a restaurant domain, you think there's something like if it's in a tourist domain, there's some kind of type of venue you're looking for. In this case, a restaurant, but it could be a hotel or a bar. And if it is a restaurant, you might want to know the food type, and there's lots of them. So each of these vertical bars is meant to represent the probability that the user wants that specific food. So in this particular example, again, remember, it's just a cartoon. It's not meant to be real, but Italian and Indian have got quite high probability. There's a don't care option, which is lower probability, and so on. So for every possible dialogue state variable, there's a probability distribution. And the goal, of course, is to get delta functions on all of these, or as close to delta functions as we can get, so that we're pretty certain about what the user wants. So after each turn, what the system does is it looks at these distributions and decides whether to ask what to do, access the database or ask a question. So in this particular case, the dialogue manager, using a policy, which is tells it what the decision logic should be, the dialogue manager issues some kind of action, which again, this is a very simple abstract notation in this case. Confirm request food. What that means is we'll confirm the stuff that we're probably pretty certain about and request the food because I don't really know what that was. And there's some kind of response planner takes this quite abstract form, adds some extra information to it, like confirm that the price is cheap and the area is east. Still not sure what the food is. So the output is, okay, so you'd like a cheap restaurant on the east side of town, what kind of food would you like? So that's just setting out the scenario. That's what our spoken dialogue system does for me. And what I've been working on for the last 10 years is trying to get to the point where every piece of that end-to-end system had no rules in it. It was a statistical model of some description, and it was entirely trained from data. And when we started working on this 10 or so, well, a bit more than that now, I suppose 15 years ago, the goal here was, as I said, it was, can we build an end-to-end pipeline trained entirely from data, no rules, and crucially exploiting the full speech recognition output? Because remember, I came originally from worrying mostly about dealing with the fact that speech recognition was pretty awful. 15 years ago, it was a lot more awful than it is today. But what we could always do is generate quite a rich distribution from the output of the recognizer. And if you were to search around in the things that the recognizer postulated, you'd probably find what actually the person said. It just wasn't the most likely thing in probability terms. So the argument then was this leads to reduced maintenance costs, not so much handcrafting of rules and deploying systems and twiddling around with them till you get them to work, improved robustness to noise and user confusion, and the ability to adapt and improve online. And so we explored various ideas and we ran tests and so on. And we've more or less demonstrated with a sequence of papers over the years that we can indeed improve robustness, and we can actually more or less do all of these things. And what I wanted to do for the next probably 20 minutes or a bit longer is just to canter through some of the techniques we've looked at in order to do this, to give you an idea of the sorts of algorithms that we use, and then to say a little bit about the bit about towards open domain, because all of my examples assume that we know what the domain is, and there's a very simple ontology or database that effectively defines what all of those state variables might be and so on, and makes the whole thing tractable. So speech understanding, an area I know a lot of people in Microsoft have been working on. This is the bit that does the mapping, and there's essentially 3 different ways to do this, broadly speaking. The traditional way is you write rules. So again, I'm using very simple examples. So in fact, probably from the first slide, I like a cheap Italian on the east side of town. You can relatively easily write some rules. A system that was commonly used 20 years ago or so is something called Phoenix. I think it was actually written by Carnegie Mellon. It's a sort of rule-based parser, but it's got features that allow you to be robust to speech recognition errors. It's a sort of context-driven word spotter, actually. And it can generate things with the right rules, generate sort of these frame-like things, which translates the sequence of words into a set of attribute value pairs. More recently, people have looked at what is now called semantic tagging. The computational linguistics community has done a lot of work on this sort of thing. The idea here is you just treat the input as a sequence of words that you want to tag with useful semantic tags. Now, of course, groups of words correspond to single semantic elements. So what people typically do is use something like what's nowadays called the BIO notation, which is rather trivial. It means that you tag words like, and the B just means begin, and I means inside, and O means something else, other. So I'd like, you might tag as in B in form, I in form, A you don't care about. Cheap Italian is begin price, Italian is begin food, east is begin area, side is inside the area, of is inside the area, town is inside the area. Maybe. I mean, the tagging depends on your own conventions. But the idea is if you can train some kind of model which, given the sequence of words X, can give you a probability distribution over the sequence of tags Y, then if you got those tags, it's relatively trivial to parse the tags and extract the information you want. People like this because it's sorry.
How did it know that Italian meant food rather than, I don't know,
Well, because you learned it from data. So what you have is you have a large corpus of data along which is tagged, and you basically learn this probability distribution. So if you've got examples in the corpus, you'll learn it. If you haven't, you might not. Sorry?
What kind of features does that use? So is it just the neighboring words, for example?
People set this up. The initial work on this using hidden Markov models was essentially just using the words like as a raw symbol sequence. And conditional random fields, which has sort of taken over somewhat, probably it's about the best, at the moment, the most accurate method we have of doing this. So conditional random field, because it can take as input a wider span of features. Typically, you put n-grams in as the tag. So it's looking at the current word plus the previous, the next, maybe the count, how many words are we from the beginning. Build your own feature set. There's hundreds of papers playing around with lots of these things. More recently, people have started to look at alternatives to this sequential labeling, of course, because this doesn't allow you to incorporate anything like hierarchy or in the linguistic sense. An alternative is to say, okay, well, maybe what we should be doing is turning the problem round, and we should be searching for things like tuples. So if I could have just designed a classifier whose only job was to look at this sequence of words and tell me whether price equals cheap's in there or not, you could design an SVM to do that. You could stick all of the words in, all of the n-grams, anything you like. And if the classifier is cheap, sorry, forget the pun, you can just have hundreds or thousands of them, and you just throw this sequence of words at them all in parallel, and those that pop up with and say, I think there's area equals east, food equals Italian in there will light up, and you can take the output. And there's various forms of this, and I'm just showing one we worked on here. Not surprisingly, with the interest in deep learning, this kind of framework's now given way to neural networks, which are being tried to do the same thing. One of the other issues is how you actually deal with multiple ASR output and the desire to generate not just one hypothesis, but a ranked list of hypotheses. So there's, again, multiple architectures for this. When we first started looking at this, we used, from the recognition, the automatic speech recognition, we generated n-best strings. And then you could just treat each string as an individual hypothesis, parse it with the SLU, whichever your algorithm was, get a list of n-best. I'm calling them dialogue acts here. This is just what we call our abstract representation. Merge duplicates, and there you are. An alternative is, and one of the problems with this kind of architecture, is that if you take the n-best list from a speech recognizer, you have to go pretty deep into the list before you pick up all of the interesting information, because lots of the top hypotheses are just small variants of each other and actually mean the same thing. So there's the various compact forms of this, one of which is what speech people call a confusion network. And it's basically, they also call them sausages for obvious reasons. You basically have a set of arcs between the dots mean sequence in time, but not necessarily synchronously. So you have a set of words, and the arcs represent alternative words, and each word has a posterior probability. So you can find lots and lots of routes through the confusion network, and you've got a posterior on each word. And from that, you can construct many different hypotheses. And from that, you can construct features which go into a single SLU and give you an n-best list. And again, I'm not wanting, I know this was sort of meant to be tutorial, but I actually want to skim over the top and give you an idea of what works and what doesn't work. And this is a test done on a data set which is collected in the motor car. It's people asking for restaurant information. There are 10,000 training utterances and 4,800 odd test set utterances. And what's shown here are the results just from those particular examples I gave you. So our sort of best Phoenix parser gives these scores. Now the F score is just the, you're probably familiar with F scores, it's the sort of geometric mean of precision and recall. It's the ability of the system to retrieve the attribute value pairs from the input from the most likely hypothesis. So you can think of it as sort of percentage accuracy in a way. The ICE score is unusual, and it's a metric you won't be familiar with. But what we've found is that on the end-to-end dialogue system, what matters most is the quality of the distribution over possible hypotheses, not the one best accuracy. If the second best was always correct, our dialogue system can do pretty well. But we would have a system which, with a very low very high one best accuracy might still not work very well. And the ICE metric, ICE stands for, what does it stand for? Item cross entropy. So an item is an attribute value pair. And this is a measure which we've found is a very good, correlates very well with overall dialogue performance. And it's a sort of, you can think of it as a sort of entropy-based metric, distance between the true underlying distribution and the distribution that the decoder's produced. So small is good. And the thing about this sequence is mostly that the F score's going up and the ICE score's going down, so they're in sort of rank order. And the numbers don't matter so much. I just wanted you to see what matters and what doesn't matter. The top two is Phoenix and the CRF, semantic tagger, using the single best hypothesis from the recognizer. And n-grams here is just shorthand for the semantic tuple classifier. So this happens to be done with using SVMs, but you wouldn't get very different numbers using any of your favorite classifier. So it's putting all the n-grams from the best output from the ASR into a classifier, and the performance is basically the same. It doesn't improve very much, or the ICE score is a bit better. We then explore what happens when you extend the list as n-best list. Adding in the second best improves it a bit. Adding in the 10 best doesn't make much difference at all, and that's consistent with what we know because there's not much extra information in there. But when we move to a confusion network, and we weight the n-grams according to the posteriors of the words in the confusion network, we get a reasonably decent input in F score. And again, another drop in this cross-entropy metric. And when we feed in some contextual information, it improves again. So as we'll see in a minute, this sort of bag of words thing is rather convenient because it opens the door to all your favorite classifier. You treat all of the inputs as you can choose whatever features you like. It's kind of quite flexible and it works pretty well. So if I move on to belief tracking, I'll come back to that point in a minute. So belief tracking is a similar problem. What's different for belief tracking is you've got state information. So remember, we're not trying to just extract the information from a single hypothesis now. We're trying to extract information from a sequence of things that the user's saying to us. And this is kind of non-trivial because if the user says "I'd like an Italian," and you recognize Italian correctly, but then you decide to confirm it, and you say, "So you want an Italian?" and the user, or you recognize no, or you think the user's negating what you just said. There's a question of do you forget altogether that the person said Italian, or do you think, well, okay, I'm not sure now, so let's ask another question. So the belief tracking is non-trivial. It gets even more non-trivial when people change their mind, which they do, of course, because you say, well, there is an Italian, but it's 4 miles away. So they say, okay, is there something nearer? Forgetting is actually rather a hard problem. What do you forget and what do you remember? So again, there are a number of different approaches that have been used for this. We've looked at 3 different. Rule-based is always a kind of benchmark system. It's not very interesting. We've looked at 2 basic schemes: a generative scheme based on dynamic Bayesian networks, and a discriminative model based on recurrent neural networks. Just to give you a flavor of the sort of things we've been doing, first of all on BayesNet, using a Bayesian network. The idea here is to decompose the knowledge you're trying to apply into different bits of information. So for each hidden variable, in this case type, in other words the type of the venue, then there is a hidden variable which represents the goal, and the goal is, in the case of a venue, does the user want a bar, a restaurant, or a hotel? Then there's a user act, so that means the last user act. So it says, did the user, is the last input from the user referring to this goal or not? Because you might want a restaurant, but you might think it's so obvious you don't actually explicitly say so. And then there's a question of what you observe, of course, is the recognition output. So you have to take account of recognition errors, and you also want to take account of history, as the user mentioned this before. And so based on the simple ontology, you can construct a dynamic Bayesian network. Other attribute pairs may depend on this. So if the user wants food, they're more likely to want food if the goal type is a restaurant rather than a bar. Some bars serve food, but less common. So you might condition the food type on the goal type. Same sort of structure. You can build this automatically from a simple ontology. And then, of course, because it's a time series, you have to link all of these to the next time slice. And I'm not showing it here, but all nodes are conditioned by the previous action or the previous question. And you can use expectation propagation such that given your observations, you can infer back what the goals were. Recurrent neural networks are rather different. Now, the problem with the Bayesian network is it's actually very difficult to get a Bayesian network to forget, at least to forget quickly. So if the user changes their mind, it tends to retain, it's rather persistent about thinking, the user wants something wants Italian, and they've changed their mind, now they want Chinese. And also, it's rather prone to suffering from correlations in the data, which you haven't modeled explicitly in the network. So it can overestimate probabilities, for example, because it doesn't have the necessary conditional links in there. So more recently, like everyone else, we've been looking at neural networks, and particularly recurrent neural networks. And again, you can set these things up in a rather simple way. So a recurrent neural network, we just encode the belief state as a set of outputs with some kind of softmax so we can interpret them as probabilities. We add some memory, just a row of hidden variables, and we have the usual kind of loop back scheme. And then for input, we can simply encode the last user action, the SLU, and we can encode this in different ways. And I've put ASR or SLU there for a reason. We started off just encoding the abstract semantic decoder output, and that works okay. And then we thought, well, why do we need a semantic decoder at all? Why don't we just feed the words into this? And so we tried that. And here's we ran, as it happened, we were involved in an international challenge, the so-called Dialogue State Tracking Challenge, which was started by Jason Williams over at Redmond in Microsoft. He did the first one, and then we followed up with a second one with a rather richer database, but again, this restaurant data. And various groups tried using it. And these are just our results, but they're consistent with everyone else's. So for this tracking problem, again, two measures. The accuracy is how accurate is the, in percentage terms, is the goal, the set of goals at each turn. So to get high numbers here is quite a challenge. So even for the restaurant domain, there are about 4 or 5 different goals. And so even if you've got a 5% probability of getting each one wrong, because you've got to get all 4 right to be scored as correct, it's obviously 70 or 80% is pretty good. And then the L2 is just the L2 norm between the distribution compared to the ground truth. So again, for dialogue systems, it's important to have a small L2 because you want the belief distribution to be as accurate as possible. So the top 4 lines here give you the performance for the baseline. It's a very simple rule-based system. The Bayesian network, which does a bit better than the rule-based system, but actually not much. And one of the problems with this data set is it does have examples of people changing their mind, and the Bayes net it really struggles with that. And then we have something called the delexicalized recurrent neural network, and that's a network that's been trained on all of the training data, but the slots, the actual values have been replaced by some kind of single label. So instead of saying food equals Italian, it's just got food equals food value. So it doesn't have to see every instance of every possible value that the user might ask for. And then the full RNN is where we add to the delexical RNN essentially another network in parallel, which is learning specific values. And you can see that, first of all, the RNN is really pretty competitive. In fact, it returned the best results of any of the systems that we tried, and from other groups as well, with one exception for which it's a bit of an outlier. Interestingly, if you throw away the semantic decoder altogether and put words directly into the belief tracker, it does even better. So we're losing interest rapidly in semantic decoding. Clearly, there's enough information in the word network, and the network is much better at deciding what to keep and what to throw away than your abstract representation is.
If you take that to its logical conclusion, are you planning to put waveforms into the network?
Well, people actually are working on this for speech recognition, believe it or not. They're now sticking waveforms directly into neural networks and trying to see what they can get from it. Chris and I have been around long enough to remember the 80s when people were trying the same things without success. It's all a bit mysterious why all of a sudden we can do this.
Be the paper that you sent to the journal, don't you really?
Yeah, exactly. Yeah. Cut out the middleman entirely. Yeah. So I see from the clock I'm taking too long as usual. Dialogue management is the partially observable Markov decision process. This is a different sort of problem. It's no longer a mapping problem or a classification problem. This is a planning problem with delayed rewards. Because if we're having a dialogue with the user, what we're trying to do ultimately is satisfy the user's request or information need or whatever. So we score dialogues based on a reward function. And our reward function is very simple at the moment. We give a significantly positive reward if we give the user the information they want. We subtract 1 from the reward for every turn, so that we're encouraging the system to learn how to do things quickly. And we give a negative reward if the system gives the user bad information. And so the goal of the dialogue management is to take this belief state distribution to have some sort of function, and this is actually a probability distribution, but conventionally in the literature, the probability of some action A given the belief state B is written with pi. And the goal is to find a pi which such that the expected value of reward you get from running a dialogue is maximized. And this is a sort of classic reinforcement learning problem, for which there, of course, is a very large literature, and you can choose your favorite algorithm to many extents. We have focused on 2 specific sorts of algorithm over the last few years. We've looked quite extensively at a direct implementation of this distribution, then maximizing it by gradient ascent. And of course, the issue there is how you actually parameterize this distribution. And we've used things like radial basis functions and similar formulations. And we've also more recently been looking at using a Gaussian process approximation, and that's the one I'll just briefly touch on now, because that's turned out to be have some really quite helpful properties. So GP SARSA is now standard reinforcement learning technique, not invented by us. And the idea here is, instead of modeling the policy directly, what you try to do is model the so-called Q function. In reinforcement learning, a Q function is a function which gives you an estimate of the expected reward given that you're in some state, B, and you take some action A following some policy pi. So you imagine a dialogue context, you're some way in the middle of the dialogue. The Q function will tell you, given the current belief state, for all of the possible actions I can take, it tells you what your expected reward is. So the obvious policy to follow is the policy which is going to maximize the reward. So the Q function gives you effectively a policy to execute. And if you have some data in the form of a sequence of belief action pairs and then the resulting reward, then this is essentially a regression problem, and you can use GP regression to solve it. It's slightly tricky because you can't actually observe the intermediate rewards. You can only really observe the final reward. And there's a neat way of dealing with that. So given some so-called trajectory, i.e. a sequence of points, then it's relatively straightforward, in fact, textbook these days, to write down what the posterior of the Q function is. And you can then sample the mean and use this to determine the policy. And if you put this in a kind of learning loop, you get something which is equivalent to the original SARSA algorithm for reinforcement learning. Again, not going into the details, but the basic idea is you have your current estimate of the Q function as determined by the GP process. You take an action, you update the belief state to the next belief state, you observe the reward, and then you update the Q function, you go round and round the loop, and you can show this actually converges on the optimal policy. In order to do that, though, you have to occasionally take the wrong action in order so that you can explore space. And one of the neat things about GP is when you're deciding when to explore and when to follow the best possible policy by just sampling the thing that maximizes Q, you've also got to know what the covariance is, and therefore you can adjust your exploration depending on how certain or otherwise you are of the Q function in this bit of space. So it all works really quite neatly. But the thing that's really useful about GP from our point of view is, whereas previously using NAC we required something like 100,000 dialogues, with GP you can learn useful policies after 2,000 or 3,000 dialogues. So it's much more data efficient. So much of our work has been done with simulators, because we started with algorithms which required way too many dialogues. But with using with GP, you can do online learning, and then you can start training policies with real users, which is where it gets much more interesting. And here's just some headline numbers on particular tests we did. Paper is here. But and this is just to give you a feel for how it works. So if we train a system on a simulator using NAC, and the user this all works at the abstract dialogue level. So this isn't a simulator that generates some speech and then waits for the system's response and recognizes it and so on. It's actually done at that abstract end after the semantic decoding. So it's dialogue acts in, dialogue acts out. If we train a NAC policy using a simulator, and the simulator we've worked on for years, so it's a real flaw in the whole thing, I can say, well, we can deploy systems that require no rules and no training and it's magic, but we did spend 5 years developing a simulator. It kind of takes the edge off it a bit. But it's a pretty good simulator by now. It's pretty realistic, but obviously not realistic enough. It doesn't represent all users. So this is a test we did over the telephone. So all the testing is real. We're not testing on the simulator. We're just training on the simulator. And we're testing with real people in the sense that they are warm-blooded humans, but they're recruited via Amazon Mechanical Turk, so their motivations are questionable. And what we do is we get people on the web page. We say, imagine you're in Cambridge and you're looking for somewhere to eat, or you're looking to sleep, have a night in a hotel, and then they call this number and get the information you need. It's that kind of setup for testing. So trained on the simulator, NAC and GP SAS are actually pretty similar, which might be what you expect. There's a large number of training cycles. But the interesting thing really is that with GP SAS we can do this online. So we can, whilst the Amazon Mechanical Turkers are using the system, we can actually collect the data and update the policy and let the system learn. And there we see a significant improvement in performance. In fact, the success rate on that particular trial was 97%. And that's with a speech recognizer, which is still making more than 20% word error rate. And the task's not entirely trivial. So, I mean, that's starting to get the level of performance, which is really quite encouraging. But the crucial bit is to be able to learn from real users rather than learning from simulated users. I think I'm going to skip generation because it's something we haven't worked on very much. I have just to give you a flavor for how these systems work. This is a video made more than 18 months ago, I guess. But it gives you a flavor of the kind of system. Now, this system is fully trained from data. There are no rules at all in this system, if I can make it work. Do I have to?
Hi, I'm going to show you our new dialogue systems technology in the context of trying to find a restaurant. So here I'll make a regular phone call to one of our systems.
You can hear it's a bit noisy.
Hello, welcome to the Cambridge restaurant system. You can ask for restaurants by area, price range, or food type. How may I help you?
Could I get some Italian food that's maybe something cheap?
You are looking for a restaurant, is that right?
Yes, an Italian restaurant.
What part of town do you have in mind?
I don't really care.
Pizza Hut City Center is a nice restaurant in the center of town serving Italian food.
Not recommended.
Is it cheap?
Pizza Hut City Center is a great restaurant serving Italian food, and it is in the cheap price range.
Could you tell me the phone number?
The phone number of Pizza Hut City Center is 012233233737.
Thank you, goodbye. So there you can see an example of finding a restaurant using simple natural language.
Okay, so obviously the first thing people do is they say, well, the synthesizer sounds terrible, and it's true. It's an off-the-shelf statistical HMM-based synthesizer. The reason for using it is primarily because I can genuinely say every component in the loop was trained by us using our data. And obviously you could connect it to a much better synthesizer. Similarly, the recognizers are a recognizer. Although using other people's recognizers is more problematic because it does rely on having a rather well-designed word confusion network output. You can see that it was a fairly noisy conditions, and it's not to say this is a wonderful system, simply to give you a flavor of the kind of system that we've been working with. Now, just for the last, the last few minutes, I need to justify the title for my talk. So from limited to open domain, so this is something that we're now working on and about to start a new research project funded by the EPSRC on this. How do we go from a system like this to a system that can talk about anything? Now, I'm obviously, when I say anything, at least initially what I mean is any topic that you could plausibly imagine designing a system of similar capability to handle. So it's not that we're trying to solve deep AI or handle sort of very rich question answering things. But if it was, if you think about what you can do on the web, you can look for restaurants, you can look for movies, you can buy shoes, you can do all of these sorts of things. They're all grounded in actually some pretty basic semantics, but the problem is there's just many, many topics. And if you had a user who just wanted to flip from one topic to another, how would you do that, given that there are thousands of topics? And although one could collect data and train a system like this on each individual topic, it would be tedious, and I'm sure the user would quickly find something you hadn't got any data for. So the particular sort of aspect we're looking at here is we're saying, okay, we have an end-to-end system. What are the key issues? What would be the real problems in scaling this to a very large set of topics? The obvious problem would be scaling, so that instead of just a few, your belief distribution, instead of being over a few specific variables, is potentially over thousands of variables, and then you'd need a huge amount of data to train it. Well, an obvious way to deal with the complexity issue is to still think of this as a very large number of individual dialogue systems. You can imagine the person speaking, and instead of speaking to one, you're speaking to 1,000 or 1,000,000 in parallel. And you just, the one that actually has any clue what you're talking about is probably the topic that you're talking about, and it produces the response. So you can think of this as also as kind of multi-domain. So a potential solution is to employ a sort of distributed representation. Instead of this one policy and one semantic decoder or whatever, just distribute them. And I tend to think of the ontology as being the framework on which I want to distribute all of my dialogues. So I imagine I have an ontology covering the whole space of interest, something like Google's knowledge graph or whatever you guys call your graph. And attached to each node in the graph is a little dialogue engine that knows how to talk about the nodes in that graph. Now, if you wanted to do that, you would have to think, well, how do I get this? And let's suppose that the idea is to collect data online and learn, as I illustrated, by interacting with the user, collecting data, improving the models. If you were to set things up like that, how would you bootstrap it? How would you deal with the bits of the graph for which there's no data? What we're looking at the moment is the extent to which you can use generic models and a sort of an inheritance idea in order to be able to execute a conversation sufficiently well that it's good enough to get the user speaking, and then, of course, as more and more users use it, you collect the data and you improve. So let me just finish with an example of this. This is the first experiment we've done. So because we've got the data and the models already. Suppose we imagine we've got hotels and restaurants, and we imagine we've got no data at all, or very little data. So let's say, well, I don't have enough data to train a hotel or restaurant, but the venues, after all, they've got a location, they've all got locations, names, quite a lot in common. Suppose I was to have just about enough data to train a model for venues. Could I use that to talk about hotels and restaurants? And if I could do that well enough, once the users have started to use the system, well, first of all, of course, I could just collect more data to get my generic venue model working well enough. And then when I think there's enough data, I can obviously just devolve this downwards, split the data set into two, one for hotels and one for restaurants, and then essentially using the venue as a prior, I can update the models for the restaurants and the hotels, and now I've got more specific dialogue relating to those two. Now, obviously, you have to do this for the understanding bit, the belief tracking, the dialogue management, the generation, and we've been playing around with those. I just want to talk about the dialogue management today. How do we design a generic dialogue policy where some of the information is different for the venue from hotels to restaurants? Of course, there could be many other kinds of venues. Well, we've actually been running some trials in San Francisco as part of another project. So we had a bunch of data for hotels and restaurants in San Francisco. And when we look at the slots or the attributes that are in the data, there are actually just 4 common attributes: name, area, near, and price. Cardinality, it just tells you can see it's a very small piece of San Francisco. There are only 239 names in this particular data set, covering 155 areas. There's some landmarks, so you can say it's near Union Station or whatever. And price is grouped into cheap, moderate, expensive. Hotels are 4 price ranges. Can't remember exactly what they are. For hotels, there's a few binary features, like dogs are allowed and has internet and accepts credit cards. And for food, there's obviously the type of food served, apparently 59 different cuisines in San Francisco. And whether it's good for meal, is it good for lunch or evening meal? And our children allowed. Okay, so how do we model that? Well, an obvious way to do it is to say, well, let's just take the slots that are common, and let's take the slots that aren't common and just give them abstract names, which might appear a little funny, but you have to remember that most of what the dialogue system is doing is trying to establish the belief on a particular slot. It's trying to construct a delta function rather than a uniform across all possible values. It's not actually that bothered what the actual slot means. It's mostly interested in asking the right question to get more information to make that. And when you look at the decisions it's making, it's actually often quite crude. It's basically along the lines of, do I know anything about this slot? or do I know quite a lot about it? And that obviously is just the shape of the distribution. So in many cases, it doesn't matter whether it's food or it's the price of petrol or whatever. It's the shape of the distribution it's actually most interested in. And that's, so what we do is so for GP, you need to define a kernel function. And so the kernel is just just tells you for any two belief points effectively how similar are they. We use a very simple inner product for our kernel function. And then what we do is we construct a kernel for the whole belief state by just summing up inner products over the beliefs for each individual slot. And since these slots have different sizes, it's very crude. We replace, we just pad out the lower cardinality slots with zeros. So we just add zeros to, for example, has internet, so that it's got the same cardinality as the other slots. So it's a very simple experiment. And what we find is I think the results are really quite interesting. So first of all, what's this table showing you? We'll just focus for the minute on the in-domain and the generic, the first and the third line. So the first line is what happens when you train two completely separate dialogue managers, one for restaurants and one for hotels, and you train them with just 250 dialogues. And you compare that with the generic venue model trained with exactly the same data set. So it says 500 here, that's just because it's got 250 hotels and 250 from dialogues. And you see that the performance is considerably better in both cases. So when something's badly undertrained, it's better to pull the data, even though it's a rather more approximate model, than it is to try to use sparse data and do what you can with the individual domains. So even curiously, and we don't really quite understand this, when you double the amount of data in each subdomain, it's still not as good as the generic model. So that's effectively with as much data in each subdomain as this has got in total. We think that's, again, because when it's sparse, you're actually better having these somewhat more abstract slots and focusing on the common slots. When you increase the data, you get a similar effect. So when you go to 2,500 and compare it with the pooled data, it's still actually slightly worse. But now when you have 5,000 in domain, it's actually about the same. Now you might expect, why isn't this better? And I think this is because this is all done with a simulator, and the simulator is not a great model for how users behave. When we actually try to run this system live, this is what happens. Actually, I've forgotten to put the success rates on here. But this is the moving average reward as it's learning, starting, and it's actually averaged over, I think, 100 dialogues in the horizontal axis, so it's somewhat smooth. So the lower curve is training a single domain from scratch, and the upper curve is starting with the generic venue and training that starting with the generic venue as a prior and then training the individual domains. And you can see that starting from the prior and then refining to this is I think this one actually is training the restaurants. So this is a venue, the generic venue prior being used as a prior for training the restaurant domain. And what you find is the reward is never terrible. It starts off okay-ish, and it actually improves quite quickly. So even after 150 dialogues, it's reasonably good. 10 is a reasonable reward for this task. This is training the restaurants from scratch. And here the problem is for the first 150 or so conversations, the system's close to unusable. The reward's negative, which means it's failing in a large number of cases. So when we measured the performance here, the system trained from the prior is getting significantly higher success rates. So this is a very early experiment. What it shows, I think, is that the basic idea is plausible, that you can deploy a system, and by using generic policies, you can provide something which is usable, so you don't make your customers suffer terrible performance whilst the system's learning. And you can imagine a system which starts off with just a few very high-level policies, a very few high-level dialogue models, and then the more people use it, the more those dialogue models get refined and become more specialized, and the performance improves. So I'm sorry I've spoken too long. This is my conclusions. I've given you a flavor of what I mean by a fully statistical spoken dialogue system. It's plausible to construct one, and we can show it works. We can show it's actually more robust in difficult conditions than anything we can do with rule-based systems. Scaling from limited domains to large multi-domain systems is constrained by complexity and the lack of data. And this simple possible way forward is to have this kind of hierarchy of policies distributed across the domains, in which you start with generic policies and then use those as priors in order to bootstrap much more and more specialized policies. I've shown you how we can do that with the dialogue management policy. We've also tried doing it for a recurrent neural network, and it's still early days, but it looks like you can do similar things with those as well. Whoops. Oh, that's the end. Sorry. Actually, I meant to just put up the... It wasn't meant to be the end. It's got one more slide, a very important one. I, of course, don't do this personally. There's a large number of people contributing to this.
All right, thank you very much for this very interesting tutorial, walking us through this impressive body of work in this area. Questions? Yeah, Chris?
Oh, we don't need this anymore. Maybe not. So, your objective measure was success in booking a restaurant, and you penalised the system, I think, for the more turns it took to get to that objective. I think I read somewhere that 95% of human conversation is not about exchanging information, it's more of a social phenomenon. If you wanted to build a dialogue system that had sort of an interesting discussion, obviously that's a much more challenging task than the one you've tackled, but any thoughts about how you might address that?
Yes, I actually haven't told you the one flaw in this, and you're probably thinking, well, I don't really believe any of the complicated stuff. But the real flaw in it still is we actually can't tell when the system was successful or not, which is sort of goes to your point a bit. It's actually very difficult to automatically get to the end of it with a real user. We can do it with mechanics paid subjects, of course, because we've told them what the task is. We can measure whether they fulfill the task or not. For real users, it's very hard to know exactly what they want and whether you've satisfied their need or not. So what we've been doing recently is looking much more at distributed reward functions, where we start to score and using techniques like reward shaping rather than changing the reward function. So looking for features that are desirable and not desirable, so presumably corrections are undesirable. Apparently making progress because you're moving from topic to topic is desirable, and giving those individual scores. So I guess to get a sort of chat system, you would have something like that. How well it would work, I really don't know, because we haven't really focused on it. We're sort of very pragmatic. We want to take the applications effectively providing the sort of the grounded semantics of what we're actually trying to achieve, and working back to say, how do we get the dialogue to drive this application? And they're mostly goal-directed things.
Other question? Yeah, Andrew?
I don't know if it's a superficial thing, but the dialogue you demonstrated and other ones that I've heard are kind of slow and heavy-handed, aren't they? They sort of repeat things, and just the speed of... What needs to be done to make it more fun to interact with?
Well, certainly one of the flaws is that humans don't adopt this turn-based. You quiet whilst the system speaks, and then you dutifully respond with an answer, and then wait for the response. I mean, real humans don't interact like that, and we have sort of done some stuff on much more what's called sort of micro-turn type stuff, where you're continually listening to the user. If it's clear that they're off track, you interrupt them. Similarly, if the system's off track, they interrupt the system. And that's much harder to do. I mean, there's a lot of engineering problems with that. But to get a system that works the way you would like it to work, that's what you have to do. You have to be continuously listening. So this idea of turning the recognizer on and off is a no-no. Has to be listening all the time. Your dialogue policies need to be evaluating at every word, but certainly every chunk. What shall I do here? Shall I interrupt? Shall I just keep listening? Or, so the policy needs to be at a much more fine-grained level. It's a very interesting area. But
So so you were talking about the simulator, and I think that is very interesting. I mean, in the future, when one sort of thinks about more subtle sort of evaluating such subtle effects, how would one go on and sort of build on these more sophisticated versions of these simulators?
Well, I don't want a simulator. I'm very eager to get rid of it altogether, so I haven't really thought about that. I mean, the simulators is what we do. We want to be learning online from real users, interacting with real systems. There's no question in my mind about that. And we have to find ways to do it.
So, but there is a natural question that you need to have some bootstrap process, right? Otherwise, the users might not even come. So there.
Or you pay some. I mean, if you only need a few thousand dialogues to get started, you pay people to do it. Still better than the simulator. And with, especially, the opportunities a company like Microsoft has for just putting online things that are games and so on, and you just get people to use them. Much better than the simulator.
Okay, I think maybe we can continue discussions over nibbles and wine, but before that, let's thank Steve for a very nice tutorial again.